Welcome to the third part of Lecture 8, Introduction to Number System. In this part, we'll discuss about byte, nibble, and word. A byte always consists of 8 bits and it can represent any of numerous type of data or information. So we can say 8 bit equals 1 byte. So there is an example given. Use the laser pointer. It says how many bytes are in 32-bit string. You have 32 bit. So 8 bit equals 1 bit. If you divide 32 by 8, you'll get the byte. So 4 byte. So 4 byte in 32-bit string. Another example is what is the largest decimal value that can be presented in binary 2 byte. So 2 byte. That means 1 byte is 16 8 bit. 1 byte 8 bit. 2 byte means 16 bit. So for 16 bit, the number will be 2 to the power n minus 1. Here n is number of bit, so 2 to the power 16 minus 1. So this is the largest decimal value that can represent using binary 2 byte. Binary numbers are often broken down into groups of 4 bits because it is half as big as byte. It is named as nibble. So that means 8 bit equals 1 byte, but 4 bit equals half byte. This is called nibble. Word is a group of bits that represent certain unit of information. The size of word depends on the size of the data pathway in the system that uses the information. The word size can be defined as the number of bits in the binary word that a digital system operates on. Now we will discuss about the gray code. Let me use the laser pointer again. So digital system operate at very fast speed and respond to changes that occur in the digital inputs. Just as in life, when multiple input conditions are changing at the same time, the situation can be misinterpreted and cause an erroneous reaction. So in order to reduce the likelihood of a digital circuit misinterpreting a changing input, the gray code, which is also known as reflected binary code, has been developed as a way to represent a sequence of number. The unique aspect of gray code is that only one bit ever changes between two successive numbers in the sequence. So if you have a sequence, then only one bit changes. Gray codes are widely used to facilitate error correction in digital communication, such as digital terrestrial television and some TV systems. So here is the example of gray code. To convert binary to gray, simply start from the most significant bit and use it as the gray MSB. You have given V0, V1, V2. This is binary bit. You need to convert this bit into gray code. So how you can do it? It says convert the binary to gray. Simply start on the most significant bit. So this is least significant. This is most significant. So take the most significant bit and put it here. Okay. So start on the most significant bit and use it as gray MSB. So use it at gray most significant bit. And regarding other two bit, how you get G1 and G0. So for G1 and G0, you need to compare these two, like B2 and B1. Comparing B2 and B1, you will get G1. Comparing B1 and B0, you will get G0. How you can get it? So it says now compare the MSB with the next binary bit. So for MSB is here B2 and next is B1. So compare these two. How you can compare? If they are same, then G1 equals 0. So if B1 and B2 and B1 is same, then G1 will be 0, otherwise 1. Say like this is same. So G1 is 0. Second one is same, G1 0. Third one is defined 1, fourth is defined 1, fifth is defined 1, sixth is defined 1, 7 is same means 0, 8 is same 0. Right? How you can get G0? So compare between B1 and B0. So if same 0, otherwise 1. So 0 0, that means same 0. 0 1 defined means 1. 1 0 defined 1. 1 1 same 0. 0 0 same 0. 0 1 defined 1. 1 0 defined 1. 1 1 same 0. Now you got it. The gray code. Here is the representation of all of the codes. So decimal 1 to 15, binary 0 to 1111, which is equivalent to 15, hexadecimal 0 to F, which is equivalent to 15, BCD 402, this one, which is equivalent to 15, and gray code 40 to 1000, this is equivalent to 15 of decimal. So you need to know this conversion. It will be really helpful for converting one number system to another number system. Alphanumeric code. In addition to numerical data, a computer must be able to handle non-numerical information. In other words, the computer should recognize codes that represent letter of alphabet, punctuation marks, and other special character as well as number. These codes are called alphanumeric code. ASCII code. The most widely used alphanumeric code is the American Standard Code for Information Interchange, ASCII. The ASCII, pronounced as ASCII code, is a 7-bit code, and so it has 2 to the power 7 equals 128 possible code groups. This is more than enough to represent all of the standard keyboard character as well as the control function. The ASCII code is used for the transfer of alphanumeric information between a computer and the external device such as printer or other computer. Computer also uses ASCII internally to store the information that no operator types in at the computer's keyboard. This is the example of different types of ASCII codes. So let's just given character. This is equivalent hexa number, equivalent decimal number. Character, equivalent hexa, and decimal number. So for all the character, you have the equivalent hexa and decimal number as well. Parity method for error detection. The movement of binary data and codes from one location to another is the most frequent operation performed in digital system. For example, the transmission of digital voice over a macro link, the storage of data in and retrieval of data from external memory device, such as optical disk, the transmission of digital data from computer to a remote computer over telephone line. Parity method for error detection. Whenever information is transmitted from one device transmitted to another device, the receiver, there is a possibility that errors can occur such that the receiver doesn't receive the identical information that was sent by the transmitter. The major cause of any transmission error are electrical noise, which consists of spurious fluctuation in voltage or current that are present in all electrical systems to varying degree. The transmitter sends a relatively noise-free serial digital signal over a signal line to a receiver. However, by the time the signal reaches at the receiver, it contains certain degree of noise superimposed on the original signal. Parity method for error detection. Occasionally, the noise is large enough in amplitude that it will alter the logic value of the signal as it does at point X, which might be interpreted as logic high incorrectly. If you look at here, this is transmitter, this is receiver. You have say 1 and 0 here, but here 1 and 0, but here is a fluctuation. So this x, this could be represented 1, which will give you wrong information at the receiver end. So many digital systems employ some method for detection and sometimes correction of errors. One of the simplest method is parity method. A parity bit is an extra bit that is attached to a code group that is being transmitted from one location to another location. The parity bit is made of either 1 or 0 depending on the number of ones that are contained in the code group. Two different methods are even parity method. Total number of 1 is even including parity bit. Odd parity method. Total number of 1 is odd including parity bit. So you have given example here. So if you count the number of 1, 1, 2, 3, 4 including parity bit. So it is called even parity because number of 1 is 4 even. If odd, then it is called odd parity bit. So parity bit, the parity bit is issued to detect any signal bit errors that occur during the transmission of code from one location to another. The method will not work if two bits are in error. It is used only when the probability of single error is very low and the probability of double error is essentially zero. Transmitter and receiver must have an agreement in advance which pair to be used, even or odd. Example. So this is the transmitted code. If you count the number of 1, so you can see 1, 2, 3. So including parity bit, you have 3, 1. So this is odd parity. But if you look at the received code, it is 2 including parity bit. So it is even parity. So which is wrong actually. It says couple of information is missing, right? So the receiver will receive even number of 1, but it is known to be receiver that the odd parity has been used, which ensures the receiver there must have been an error of 1 bit in the received code. This is the example, couple of example we already discussed. So it says convert the following to hex then binary. So you have given the decimal number 757.25 into convert it to hex and then binary. So 757.252. So converting to hex. So divide by 16, you will get this one 2f5.4, and if you convert it to binary, you will get something like this. So we will discuss this in the class actually. So this is a class work. So the procedure we have discussed before. So I'll suggest you to show the whole calculation and check with the results whether you got the same results or not. Similar thing 123.17. So divide by 16, you'll get this hexa and hexa to binary. So convert this hexa to binary, you will get something like this. Convert the following to octal and hexadecimal. Another class work. Okay. So you have given the binary, so you need to convert it to octal. So make a pair of 3 bit, write the equivalent octal number, right? And it says then octal to binary again and binary to hexa. Okay. The second part is same, decimal to octal, octal to binary, binary to hexa. When converting binary to hexa, make a pair of 4 bit, write the equivalent hexa, you'll get the hexa to binary to hexa. Okay. And again hexa to decimal. So just divide by 10, you get the hexa to decimal for both cases. So I suggest you try to do it by yourself and check with the solution here. Thank you.